Hi everyone, James again. This time we have problem 1 of homework 8. It's the problem of finding the B field at the center of this loop. And there's current flowing through the wire that goes around the loop and then continues. So we use the fact that B fields, magnetic fields, add. We take the field that the loop would produce at the center, and to that we add the field that the straight line wire would produce at the center, and the sum of the two will be the field at the center. So it's just taking the straight wire, which has the current like this, and the center of the loop is a distance r from the wire. So we want to find the field here, which is at the center of the loop of radius r. So we find the field in this situation and the field in this situation, and then add them. And if we look at the picture, if the current is going left to right, then it's going to go around the loop in the clockwise sense. So the current here is going this way. And we want to find the directions to see if the magnitudes will add or subtract. So I use right-hand rule 2, and it's a nice problem because it illustrates both versions of right-hand rule 2. In the first version, I'm given the straight bit, which is the current, and I want to find the curly bit, which is the B field. And so if I put my thumb in the direction of the current, and I curl my fingers around to below the current where P is, my fingers go into the page. And so the B field here is into the page at P. Likewise, I can apply the other version of right-hand rule 2, in which I'm given the curly bit, again the current, and my thumb gives the straight bit, so the curly bit is going clockwise. My thumb points into the page, so the clockwise current produces a B field that is into the page at the point P. So the B fields from the two portions of the wire, the straight part and the circular part, both produce B fields into the page, and so the magnitudes are going to add because the two vectors are in the same direction. So the magnitude of the sum of the two vectors is the sum of the magnitudes of the two vectors. Okay, so in this case, we use the fact that B is mu sub naught I over 2 pi r, where r is the distance from the wire and I is the current in the wire, and that's for a long straight wire. And for the circular part, at the center of the circular loop, we have a B field which was derived in class from B sub r, I would imagine. B field that is mu sub naught I over 2r. Again, r is the radius of the circle, I is the current. And so the total B field, because the two vectors are pointing in the same direction, has magnitude, which is the sum of the magnitudes. So mu sub naught I, in fact, I'll take the common factors out. Mu sub naught I over 2 r. So mu sub naught I over 2r is common to both. And then this has a 1 over pi. And this is just as a 1. And so if I plug in, I get mu sub naught is 4 pi times 10 to the negative 7 Tesla meter per amp. The current, well, we're not given a number, so we just want to find the algebraic expression. So scratch that. And this is the magnitude, and the direction is into the page, and that's it. And notice that when it says find an expression for the magnetic field vector at the center of the loop, it means both the magnitude and the direction. So we found the direction not only to show us that we could add the magnitudes to get the total magnitude because the directions were the same for the two B fields, but also to get the direction of the total B field vector. All right. Well, thank you for listening, and I hope that's been useful. And have a nice day, please.